Morning, everybody. We want to address the challenge problem in yet another thrilling Physics 124 video. In the challenge problem, we have a nice frictionless table with a block attached to a spring. The perfect storm for simple harmonic motion. We're going to then shoot the block with a bullet of mass little m, right here, and it's going to start moving here from a position x equals 0. And it's going to compress to some position given here in the problem, 0.315 meters. What we want to know is how long does it take to get there? To actually figure this out, we're going to have to use the equation of simple harmonic motion to figure out where this block is going to go. Now, we're going to work this as a chain of problems. First, we have the mass of the bullet and the speed of the bullet, and we need to figure out how fast the embedded bullet plus block starts moving at x equals 0, t equals 0. To do that, that's a perfectly inelastic collision. So I can write down that the mass of the bullet times the speed of the bullet, as given in the problem, is going to be the combined mass of the two objects, m plus m, times the final speed after the collision, which turns out to be the initial speed for the harmonic motion. So from that, we can go ahead and say that that is m times v over the sum of the masses, m plus m, times is equal to the v final. So that's how fast this system starts moving from x equals 0. And it's going to move in simple harmonic motion since it's attached. So we can say that x of t is equal to some amplitude, not yet known, cosine of omega t plus phi naught. And if I knew a, omega, and phi naught, and I could figure out t if I'm given x. Therefore, we've got to start picking these apart. Of note, I have to include a phi naught, because if I think about the graph of this motion as a function of time, that's totally a straight line, right? Where this is x and this is t in terms of this position here. It starts here at 0 and then starts undergoing oscillatory motion. And we've got to figure it out when has some amplitude a, and this is not our usual situation where we start at cosine with a cosine function at a and start oscillating downward. We're starting here at 0, so that means we've got to include this phi naught term. That is what makes it a challenge. Okay, so we know how fast it's moving at the beginning of this motion. So what we're going to do is start to figure out the rest of these things. We need how fast it's moving because that's related to the amplitude, and it's related through the energy. We know that the energy for a simple harmonic oscillator is 1/2 Ka squared, and that's equal to the sum of the potential, spring potential, and the kinetic energy at any point in the oscillatory motion. In particular, it's true at t equals 0, where the spring is not compressed. So that is going to be 0 because the spring is not compressed. The spring is at its equilibrium length. Therefore, it's just the kinetic energy. And so that's 1/2 m plus big M times Vf squared, where we've already calculated what Vf squared is. And then I can go ahead and say that that's 1/2. This m plus m cancels one down there. So it's m squared v squared, where little m is the bullet mass, over m plus big M. Okay, so that gives me that in terms of 1/2 Ka squared. And I can go ahead and solve for what A is. So A must be m squared v squared over k times the sum of the masses, all raised to the 1/2 power. Okay, so we know an amplitude. Look, we can figure out omega. I'm going to use this beautiful little white space over here to know that omega is the square root of k over the sum of the masses, because both things are moving together, Let's make that a little bigger. And these are all given, all known. And then the last thing is this phi naught. That phi naught is going to be whatever phase constant I need so that this is the graph that I get out of it. So we know that at t equals 0, x equals 0. And we're going to get that x equals 0 equals amplitude times the cosine of 0 plus phi naught. And so then I have to ask, well, 0, I can divide under by a, and I get the equation that cos phi naught is equal to 0. And that's true for phi naught equal plus or minus pi over 2. Now we're going to pick phi naught equals minus pi over 2. And that's true because if I pick phi naught equals plus pi over 2, that corresponds to the point when the velocity is going downward. Let me draw a cosine curve here so we know what we're talking about. Here it comes up, goes down, it does a little loop. This one is plus pi over 2, and this one is minus pi over 2. And this is the point that I pick so that we get a curve that looks like this going on. And so therefore, we now know that phi naught is negative pi over 2. We know an amplitude. We know an omega. All these things are given in the problem. And then it's solving a trig function here for time to figure out your answer. And at that point, you should have bested the challenge, provided, and I got to say this again, radian mode. In fact, I'm going to write this down. Use radian mode for this unit here. And because it's the end of the term, have a happy family.